Right, hopefully we are live. Welcome, folks. This is the first virtual installment of Cloud Native Manchester, although the whole region thing becomes a bit irrelevant given that we're Cloud Native nowhere right now. Oh, we seem to have
We've lost Andy already.
So that's a great sign. Cloud Native nowhere right now. Oh, we seem to have lost Andy already. So that's right now. Right, enough of that. Technical glitches there. Right, well, hopefully we'll get Andy back at some point before his talk. Luckily, he's second in the running order, so I'll add him back in now. There he is. Hello.
Good evening. Yes, I dropped off momentarily.
So, how are we all doing, folks? How's lockdown treating us?
Pretty boring.
I've had better 6-week holidays. Put it that way.
I mean, there was a bit of me at the back of my mind that thought, oh, this could be quite nice being at home for extended periods of time. But after this long, it starts to grate a little bit.
I work from home most of the time, but it's the time outside of work where I wish I could leave it. Yes,
indeed. So, Andy, you work for Sky Betting and Gaming. Have you seen a huge rise in people wanting to throw their money at you over the last?
Oh, crikey! Ask me the confidential question. Why don't you? I think we've seen people change their habits. Let's put it that way, and I'll leave it at that because I don't want to get in any trouble.
Well, I think we've got two talks today. We're kind of not quite sure how the running order is going to work. I think we'll probably just shoot the breeze for 10 minutes or so, and then move it over to Tim for his presentation. So what have we got to talk about, folks? Nick.
You're going to pick on me. Well, I guess the last few weeks in lockdown has given us all plenty of opportunities to learn new things and to maybe spend some time getting stuck into technologies and playing around with a few things. So I don't know if anyone's got anything interesting that they've come across recently, interesting projects that they've had a chance to hack on.
I've had some extra free time. Not going out means that I have been working on home automation. So I can turn my lights off and on again.
Nice.
I bet the switch is just there as well, isn't it?
The switch is actually down behind a corner, but yeah.
Okay, a worthwhile bit of automation now.
So yeah, that's all running on a Raspberry Pi in another room.
Cool. What about yourself, Andy?
I'm hoping once this evening is out of the way, and it'll be the second time I've done this talk, once internally, but the last few weekends have been a labour of love. Not to want to say poor me for having to write a talk, but yeah, I've been working on this actually, so I'm really glad to get it showing today, so people can give me some feedback and let me know what it's like. But yeah, I'm not sure what I'm going to do with my free time. I've got an urge to do another certificate, but I might not. I might have a break for a bit. I might just, I was going to say sit in the garden, but I can't do that this weekend because it's gone rubbish.
Stay at home.
I might, yeah, I'll have a staycation.
I tell you what, I the one thing that really made my week this week, I don't know whether anybody else saw it, was the Goonies cast and crew reunion on YouTube, which was an absolute work of genius, where a US comedian brought back all of the cast of the Goonies. They were doing scene reenactments, talking about the whole experience of shooting the Goonies. It was absolutely brilliant. I had a tear in my eye at many points during it.
Yeah.
I'm loving the way that panel game comedy and different shows have adapted to be able to make themselves from home. So Have I Got News For You has been running for something like 25 years and is now broadcast from people's homes.
Right.
Kind of the MASH report, same sort of thing there.
Very much like this.
Yeah. Except with more talent, I would posit.
Not when it comes to anything cloud native.
Yeah, Nish Kumar, I don't know how good he is at debugging problems with DNS. He might be great, I don't know, but yeah, maybe not.
So I guess if we've got got nothing else fantastically interesting to talk about, we should probably pass it over to some of our speakers to actually do some talks. Are you in a go situation there, Tim?
Yeah, I'm ready to go.
Right, let me just drop Andy out for a second. We'll see you after Tim's talk, Andy. And if we do that, and I'm not going to introduce you, Tim, because I'm assuming you're going to introduce yourself. So I will. I now drop me and Nick out, and the floor is yours.
Okay, well, hello, stream people. I'm Tim, self-introducing here, self-isolating as well. I'm a consultant at the Scale Factory, and I'm going to talk about controllers and operators in Kubernetes. So I first want to say that if you've got the ability to file comments on the chat, you can do that live, ask questions in the chat, and we can follow those. From my perspective, it's fine to ask questions about the talk at any time, and I'll try and pick those up. So a little bit about me, I guess. I work for the Scale Factory. We're a cloud and DevOps consultancy, Kubernetes certified service provider, AWS Advanced Consulting Partner. My role in Kubernetes is that I'm a contributor, and I'm one of the technical leads for the documentation special interest group. Hey, people in the comments. Obligatory credits slide. Here are just some of the things that I've used, and I'm going to credit them properly. So what am I going to do today? And this is where I need some help from Nick and Matt. I'm going to create a deployment, and I'm going to scale a deployment, and I'm going to do a demo. So, Matt, can you, when I stop sharing, switch to my other sharing setup? Which is just loading. Cool. Okay, this is the online equivalent of looking for the HDMI cable during the talk. Okay, Matt/Nick, I am ready. Thanks very much. Okay, so yeah, I said that I would create a deployment. Let's do that. Okay, and I said that I would scale it out as well. Great. And so what this talk is going to be about is what happens when I do that. The demo is easy. I'm going to talk about what's going on in the control plane in terms of the control loops that make that possible, and I'll talk more about that. So, what's happening when I create a deployment and scale a deployment? Thanks very much. Well, first of all, I created a deployment object. So I used kubectl to talk to the API server. Every deployment I create, every time you create something using kubectl, you're storing an object into the API server. And now there's a thing called the deployment controller. It sees that there's a new deployment object and creates a replica set. So please feel free to give me feedback on level. If you're an expert on Kubernetes, I'd love to hear if I've missed out a detail or you think I'm wrong. And if you're new to Kubernetes, feel free to ask any questions about what's going on. If you'd like more detail, I'll be happy to add it. The role of the deployment controller is to take this object and create a replica set. So deployment and replica set have a job of running the right number of pods. And deployment uses replica set to create pod API objects. The scheduler, another Kubernetes control plane component, decides which kubelet will run that pod. And once that's settled, the kubelet runs the pod. Now, when I scale out the deployment updates the replica set and creates more pods. And most of the clever bit there happens not in the kubelet, certainly not on my computer, but in the control plane. So all those objects, as I mentioned, are in the API server. The control loops that I'm going to talk about here are in the Cloud Controller Manager, or Kube Controller Manager, sorry, top left. Cloud Controller Manager is really just for talking to your cloud provider, and I'm not talking about those things particularly today. So Kube Controller Manager, top left, is what's connecting those different objects. For example, connecting a deployment to a replica set. And if you're not sure what I'm talking about by controlling, I'm going to go back to a really simple example. I'm going to talk about thermostat. You can think of controllers like real physical devices, like a heater controller. So you've got an actual state, like how warm my room is that you can measure, and you've got a desired state. So if you've got a thermostat, you're talking about, I'd like it to be 24 Celsius, please. And these run in a control loop. So measure the temperature and decide whether to turn the heating on or turn the heating off. That's a really simple thing, but it's got a desired state and an actual state. And nearly every Kubernetes resource, like deployment and replica set, and pod, and many others, have that same concept of a desired state, which is called a spec in Kubernetes, and an actual state, which, depending on how the object works, it looks different. For example, replica set looks a bit like this as a loop. So a replica set has been given a way of finding the pods that the replica set is managing, matching them by label. It counts them, looks at how many healthy pods it's got, and if there's not enough, it creates more pods. If it's just right, then great, Goldilocks, go back to the start of the loop. And if there's too many pods, that remaining pod is not needed. Replica set is simple. And part of Kubernetes philosophy is to have simple controllers and implement complex behaviors by combining these simple controllers. Yeah. The idea of building complexity from simplicity comes from robotics and cybernetics. So if you were making, say, a home automation operator in Kubernetes, you'd need to take care of a lot of control loops. You want to set your room temperature. That means you need to take care of heat demand. And you can zoom in on detail. In this example, the heating system uses valves on the right hand of the slide to control how hot water, heated by the element that's at the bottom right, flows around the system. But just managing the valve system involves a lot of detail as well. So in cybernetics and automation outside of the cloud, you want to set the position of a valve. There's actually a bunch of control loops that happen here as well. If something wants to set the valve to the closed position, then there's a set of different levels of detail about how that's implemented. And I think that mirrors, or I want to make the point that that mirrors how something like a deployment works as well. So, back to the deployment. If you create a deployment, the deployment creates a replica set and it manages pods. So, why is there this indirection? And there's two different control loops as well. There's a deployment controller that understands about deployments and replica sets, and then there's a replica set controller. And the replica set controller understands about replica sets and pods. Well, this extra indirection lets you roll out a change without deleting the existing pods. That would be bad. If you want to upgrade your application, you want to be able to change the container image that's running inside a pod. And you want to do that without deleting the application and having an outage while you do that. Here's what it looks like as a manifest. So this is So this is a deployment. Let's say we change the container image, there's just one container in the pod here, to a later version. So as I say, it's important to be able to keep the whole service running. You want someone who's listening, you want someone who's connecting on port 1234 to be able to see traffic served, even if we're replacing pods while we do that. And so you create a deployment, you reconfigure the deployment, and the deployment creates a new replica set that manages pods. Adding complexity to this picture quite a lot, I'm going to talk now about how you can handle scaling. Now, I showed earlier in the demo that I could run kubectl scale deployment/example and set the number of replicas to 3. So that's horizontal scaling. I'm actually going to talk about vertical scaling. So what I mean by vertical scaling is setting the resource requests right for a pod. So what I mean by resource requests, if you've not seen that, the stuff in bold at the bottom of this slide is the resource request. So as a developer, let's say I've decided that I think this needs 128 megabytes of memory and one CPU. Is that the best placement? We can use automation. We can use a control loop to decide how much resource each pod should have and give the scheduler a much better hint about how to place pods onto nodes to make use of resources effectively. So let's talk about that vertical pod autoscaling. On this diagram, there's several control loops happening. Kubelet is a control loop. Kubelet is told about pods, looks at the API server and finds out about pods and makes sure that the pods work and then reports back its status. Deployment controller finds out about deployment objects from the control plane and makes sure that the right replica set exists. If deployment's doing a rollout, then there might be 2 replica set objects and each of those is managing a set of pods. And whilst this is going on, vertical pod autoscaler is managing, well, the resource is called vertical pod autoscaler, but really I want to talk about the control loops. So here I'm showing 2 of the control loops that are part of vertical pod autoscaler. There's a recommender. So what the recommender does is it examines a set of running pods. It finds out from a monitoring system that's looking at the kubelet on your cluster how much memory and how much CPU those pods are really using. The vertical pod autoscaler overall has a job of making those pods be the right size. So this deployment has an initial spec that you saw with a request for 128 megabytes of memory and 1 CPU. You can see that at the bottom of the manifest. Now if I run this with the vertical pod autoscaler, there's an admission hook that changes the spec for pods. So let me show you that a bit more. There's 2 bits of the controller on this slide. There's a control loop that's working out what recommendations to make by finding out data from the kubelet via the monitoring system and then storing that into the actual state of the vertical pod autoscaler. So the recommender's actual state is a set of recommendations. The admission webhook is another detail. The admission webhook looks at pods that the replica set tries to create. So let's say the replica set adds another pod and it sends it in with the request that we saw in the manifest. It sends it in with 128 megabytes and 1 CPU. Now this is where the admission webhook has a different idea. The admission webhook overwrites the resource request that the replica set thought of and says, no, I've got a better idea. And throughout the control plane, there are lots of small mutating webhooks that act to implement the behavior of a controller by making changes like this. And that gives you an idea, or I hope it gives you an idea, that there are many small bits of behavior in the control plane that together implement the complex behaviors that you see from Kubernetes. If you've got questions at this point, feel free to add them into the comments and I'll try and pick them up. So that's autoscaling. But there's a second side. I talked about the recommender and how the recommender sets a set of recommendations onto an object in the API server, and how a webhook uses those to mutate the incoming pods. But what about if you've got the pods already running? So how does the control loop and how does the vertical pod auto-scaling resource make sure that the running pods for your workload get the right amount of resources? It's actually really simple. The vertical pod autoscaler updater just evicts pods that aren't at the right size. And this works because there's other control loops running. Specifically, the replica set control loop is running. And when replica set sees that a pod is missing, so let's say I had a scale of 3, I wanted 3 running pods. When replica set sees that 3 pods are supposed to be there and that one of them is missing, replica set creates a new pod. At this point, the admission webhook I talked about kicks in, updates the pod so that the resource request is correct, and then the loop is complete. And so here we have a complex behavior of automating the resource request for pods in Kubernetes, really using only 4 control loops: the kubelet, the deployment, replica set controller, and vertical pod autoscaler. I'm going to move on, and I'm going to talk about operators. The inspiration for operators comes from the humankind. So human operators have deep knowledge about system behavior. They know how to deploy, upgrade, and decommission an application. And they know how to react to problems when they occur. And so people who understood about using traditional ways of operating things manually wanted to move beyond sort of configuration management. So if you might not have done this before and aren't using the operator pattern to manage your workload, you might have used a tool like Chef or Puppet or Ansible to think, well, I'm not going to deploy my workload manually. I'm going to use Puppet so that not only will Puppet deploy my workload, but also, if there's a problem, Puppet will drive it to the desired state. Well, that is great. It's different from Kubernetes and it adds complexity. Do people want to run Puppet in containers? That's probably not the right pattern. So instead, the idea of an operator is to use the same control loop pattern and add custom resources into the API server and have your own control loop that manages the details of your workload. So some of the operators that you might have, these are 4 real operators, will do the initial setup for a workload. So if it's Couchbase, that doesn't just mean running Couchbase. It means getting hold of the storage. It means setting up the storage for Couchbase. Yes, it means running the application as well. But it also means making sure that it's backed up and taking care of upgrades. Let's say you're running the PostgreSQL operator and a new release of Postgres comes out, Postgres 12. As much as possible, you want to be able to tell the control loop that you'd like to upgrade it to version 12 and sit back whilst a whole load of automation takes care of that for you. And that's what operators let you do. Of course, if you don't see the operator that you want, you can always, with just lots of your own time, write your own operator as well. And I'm going to talk a little bit more about one of the details there. I talked about backups. So how does an operator like the Postgres operator run backups? Well, I haven't looked at how it works, but I hope that it uses existing resources. There's a resource called cronjob. So the right way to do it is a bit like the Unix philosophy. In other words, compose small components. So here's the control loop for cronjob. Cronjob is a really simple controller, probably too simple. It's likely to get rewritten in 1.19 or 1.20. It finds cronjob objects, and these describe jobs that need to run at a particular time. If cron job finds a cron job that's due, it creates job. A different controller, imaginatively called the job controller, creates the pods to make that work happen. And then the other side of the cron job controller is to go along and look for jobs that this controller created. In other words, not just any job on the system. It's not a good idea for the cron job controller to delete every job that it sees. Just the ones that the cron job controller knows that it created and that are done. And to stop the API server filling up with stale objects, cron job will delete the job. And that'll also clean up any old pods if necessary. So notice how cron job doesn't know about pods. Replica set does know about pods. Deployment doesn't know about pods. There's the indirection. Replica set and job manage pods. Deployment and cron job manage an intermediate resource. So I'm going to recap. Controllers are a big part of Kubernetes control plane behavior. The API server defines the resources for your cluster. Controllers define the interactions between those resources, automated interactions. Human operators who look after specific applications and services often have a deep knowledge about their behavior, how to deploy them, and how to react if there are problems. And there's a name for adapting that knowledge to automation, the operator pattern. Thanks very much for listening so far. If anyone would like to ask questions, now is a great chance.
Tim, I just wanted to ask, all the interactions between the controllers, they all go through the API server, don't they?
So everything in Kubernetes, if you like, goes through the API server. So yeah, that's a good question. Oh, that's not the right slide. You've got a Kubernetes cluster. The kubelet doesn't know about the control plane except the API server. kubectl on your machine only knows about the API server. And the control loops inside the controller manager talk to each other through the API server as well. There are certain exceptions. I showed how, in fact, with the vertical pod autoscaler, there's part of the metrics there go via a side channel. So let me show that. Nothing's talking to things directly, but here with the monitoring, let's say you have Prometheus as your monitoring solution. The recommender knows how to talk to Prometheus, and it does that using Prometheus's protocol. And Prometheus knows how to scrape kubelet, and it does that using open metrics. There's also a special case of the storage controllers. Kubernetes a while ago decided to take lots of independent control loops and combine them into a single process. So that isn't lots of processes communicating directly with another, but it is lots of, I guess you could call them Go routines or elements of one control loop that communicate with each other. And that was done because people were finding it too hard to write independent loops that were bug-free for storage. Any more questions or feedback?
So there's a question in from Benedict Wilson who asked, did you write your own operator? And if so, what is your framework of choice?
Okay. Well, as a consultant, the usual answer is to look at for me, is to look at the client's team and work with them to understand what's going to work best for them. But not knowing too much about the setup, there's a thing called the meta operator. And that works by letting you write webhooks that implement the different stages of and interactions between things. And if I didn't know anything about the context, I'd say start with meta operator. But there are going to be a bunch of different things. One of the nice things about not having to deal with the rest of the Kubernetes control plane is that you don't have to write things in Go. So let me go back to the slide I had up about the control plane. So if you needed to integrate with the scheduler and the API server, the Kube Controller Manager and the Cloud Control Manager, you'd almost certainly have to write Golang code. In particular, the API server is something that's really, at the moment, difficult to implement in a language other than Golang. People have talked about it, but the libraries aren't there. However, that's not the world that we're in. We're in a world where you can get all these rich behaviors simply by talking to the API server. And so that means that if you want to use JavaScript, if you want to use .NET, if you want to use Python, Golang, Rust, all of these are valid options for writing a controller. You can even switch languages. So I talked about how the vertical pod autoscaler is actually multiple loops. There's 3 loops. There's the admission webhook part, which watches for recommendations and makes sure they're applied. There's the recommender itself, and then the updater. If you wanted to write those in different languages, or you had a good reason to do that, you could. Oh, gosh. I'm glad everyone's okay.
So I thought that was great, Tim. Thank you for that. You know, I really like the focus on how you can get complexity out of building up lots of simplicity.
Cool. I'm happy to take some more questions if you want to put time into that, or I'm happy to move on.
So one other thing that I thought might be interesting for folks to talk about, Tim, you said at the start that you're involved with SIG documentation.
That's right. So if you go to the Kubernetes website, k8s.io, then that website is a Git repo. I'm a contributor and an approver, and it's one of the most popular Kubernetes projects. What did you want to ask, Matt?
Well, I was just going to say more of a comment, really, that for folks who are looking to start getting involved with upstream open source projects, documentation is a great place to start, because there's always more work needing to be done and not enough people to do it. And, you know, it's a good way of starting to get involved in open source projects without necessarily having to really understand a big code base all at once.
Well, yeah, I certainly agree with that. A while ago, I'd have said that I'd have been quite happy saying that the documentation project is particularly welcoming to people and makes a huge effort to welcome new contributors. Now, I would still say that, but I'd have to be slightly wary of blowing my own trumpet, because I've gone from being a new contributor in the last year to being a maintainer. But yeah, if you want to join that particular SIGDocs website repo, so it's Kubernetes/website on GitHub, then I hope you will feel really welcome, and there is a curated list of first issues that will guide you in if you want to do that.
And are there regular SIG meetings as well, or is it really just to jump into the code base and start raising PRs?
So every Tuesday there is a SIG meeting on Zoom as well. It's been remote, so Kubernetes SIG meetings have been on Zoom for ages. Kind of lockdown friendly.
I was just going to see whether I could bring up the SIG docs page just on screen here. Let's just put that up so folks can have a quick look at it.
Brilliant.
And that has all of the details about when the community meetings are and all that kind of stuff, right?
That's the bunny. Yeah.
So it's just oh, there we go. It's on there. So that's got all the details of the SIG meeting times and all the rest of it. Okay, let's get rid of that. So I guess this is kind of the point in the proceedings where we would normally be encouraging you all to go away and drink fine craft beer and eat Bolton's finest pies. But unfortunately, that's one of the drawbacks of the virtual world. So I hope at home you're finding some opportunity to do that. And I guess we'll move on to the next bit of excitement of today's proceedings. Andy Bergin, hello again. Hopefully we've solved all our technical problems now. Again, Andy, I probably won't introduce you. I'm sure you'll introduce yourself, and looking forward to your talk. Let's get all set up for that. I'll just drop you out there, Tim. So we'll speak to you later.
Does Andy hold the title of the only person who will have spoken twice at Cloud Native and Kubernetes Manchester as of today?
That may be. I think he might.
I think that might be true. That might be true.
An auspicious honour, thank you.
Indeed.
Having said that, we haven't started the talk yet. This could all go terribly wrong. So,
It's time for it to cut out yet.
yeah, my Mac just decided to turn into a hovercraft just before that. So, as all Kubernetes folk know, what you do is you stop Docker at that point. So, yeah, it seems to calm down. So, yeah, I think I'm okay.
When you find 10 containers that you forgot were running in the background somewhere, chewing away at memory.
Probably yes. Okay. Yeah. So if you would like to share the old desktop, I don't know if I do that or you do that.
So you
share the screen. There we go.
Share what you need, and then I'll add you in, and then I'll.
Okay. There we go. Right. Okay. Looking good.
Right.
It might even work. All right. Okay. Well, good evening, folks. Welcome to the talk. I know there's probably a few people from outside of Manchester. I know the organisers were hoping to get people tuning in from as far away as Didsbury and possibly as far as Oldham as well. So wherever you're from, you're very welcome to be here this evening. I'm going to talk for roughly about 40 minutes on visualising complex systems. So let's move on to the deck. Before I do that, I should probably introduce myself as Matt alluded to. So hi, my name is Andy. I have been at Sky Betting Gaming for the last 6 years. For those of you that don't know, Sky Betting Gaming is an online bookmakers. We are the UK's most popular. We have sports betting products, and we also have a number of online gaming entertainment things as well for you to play with. I am lead platform engineer in the infrastructure platform engineering squad. My pronouns are he and him, and my Twitter handle is on the screen there. But if you want to ask any questions, then throw them into the chat as well. I will probably take questions at the end if that's okay, just because I've got quite a lot to get through. So hopefully we'll have plenty of time at the end. I predominantly work with Kubernetes day to day. I am the organiser of the DevOps meetup in Leeds, and also on the organising team of DevOps Days London, which, all being well, will happen in September, the 24th and 25th. If it does, it'd be great to see you there. But I mentioned the DevOps conference because I'm starting this talk with a talk from another DevOps conference. So I was lucky enough to be in San Francisco in 2017 at Enterprise Summit. And John Osborne was there, and he gave a talk called How to Keep Your Systems Running Day After Day. The link's on the screen, but all the links in this deck I will share with you afterwards, so no need to scribble anything down. In his talk, he explains, amongst a whole bunch of stuff, why the understanding and interactions of humans with complex systems are something we heavily rely on. And what he alludes to is he talks about above and below the line. So below the line are where our systems live. We have our stacks, we have our tools for deployment, our repos, our pipelines, the monitoring, the logging platform, and our applications as well. And above the line is where the humans live. And they have knowledge about how these systems work. There'll be documentation, there'll be diagrams, but we hold a lot of this stuff in our heads, including the context of what that stuff is. And that might vary between people as well. And John makes a point that this is so important because in reality, none of the stuff below the line really exists. It's all at the end of the day is just electrons moving around circuit boards. You know, you can't go and pick up a message queue. You can't see code running. And therefore, this knowledge that the humans have in their heads and that understanding is so much more important than we perhaps give it credit for. And he goes on to talk about something called the Stellar Report, which is a report on by a load of thought leaders in sort of incident management space about how better to equip people and engineers to deal with complexity, particularly in the case of an incident. So if there's a problem. And there's 6 themes that came out of this report. And the one that really struck a chord with me was number 4, supporting work through improved visualizations. Now, I've always been a bit of a data nerd. Used to like fractals back in the day, and I've done a few bits of data analysis, and I've spent some time working with Hadoop as well. And the visualization of data is a thing I really quite like. So what tools do we have at the minute to help these poor humans visualize these complex systems which we're working in to help support that stuff they hold in their heads? And you might think from the title of this talk that I actually have a problem with dashboards, but that's actually quite the opposite. I really love dashboards. I think, you know, tools like Grafana and the other dashboarding tools are brilliant. What they've done is they've made it a real simple way to provide real-time information on screens around offices or on your desktop about the state of a system. And I think that's really, really good. And there is nothing wrong with a good dashboard for me. And this, in my opinion, is a good dashboard. It's very succinct. It's got the right information in there. I can easily read it and understand it. It's a good dashboard. And for me, dashboards are a bit like jokes. If you have to explain it, it's not a good one. And taking some examples off the Grafana dashboard site, suddenly these dashboards aren't always succinct, small visuals of the state of a system. They're turning into live data documents with loads of graphs with all the information there. And there's a lot of noise in some of these graphs. The examples on the screen here, we've got some that might indicate there's a problem, some might not. Just taking an understanding from a graph like this can be really difficult at times. But for me, the thing thinking about a complex system isn't these data points in time from various metrics points that we scrape. There's no real understanding here of how the system is put together, the interactions, the components that are there. There's no structure. We can't see the structure of the application. We can't see the relationships and the interactions between these components. And that's one of the reasons I really like Kubernetes. It's a structured way of developing stuff. Now, Tim's just spoke in some detail about deployments and replica sets and these intermediate resources that exist alongside all the other ones. And I think having this structure there and a way to define an application and put it into a manifest is a really powerful way to structure. But how do we visualize this stuff when it's not a dashboard? What else do we have on top of dashboards? Well, maybe this is your visualization tool. Yeah, it might work for you. But you have to do a lot of digging to find out what's actually running and what's actually there. We can probably do better than this. And if you take nothing from this talk, my tip of the day is -A is a replacement for -- all -namespaces. You can use that tomorrow when you get to work. Okay, so how do we pull all this structure of Kubernetes objects and indeed the applications that are running on it into a thing which we can help us visualize? Well, one way of representing these workloads is through graphs. And when I'm talking about graphs, I don't just mean bar charts, pie charts, histograms. I actually mean these kind of graphs. And in this graph, this is, say, for example, somebody's Facebook friends, which was a very popular thing to generate sort of 10 years ago. In this example here, we can see the communities of somebody's friends. We've got it colored. We can see the relationships between the communities, so we can kind of tell who's workmates and who's school friends and that kind of thing. And maybe we size them by how long we've known the person. And a few years ago, these were really popular to render out and post onto Twitter with the hashtag data science, which for me only had 2 purposes. One, for people to show off how popular they were, and the other one to really upset people who were doing proper data science. But anyway, but graphs are really useful, and they're really simple as well. We have nodes, which are the blobs, and we have edges, which are the relationships between the blobs. And that node might be a person who has some attributes, might have a height, a weight, an age, or a favorite color. And they may have a relationship towards another node. So they might like somebody, and that can be directed because the other person might not like that person. And it can be weighted. Someone might really like someone or not very much. And there's a whole science built around this called social network analysis and graph theory that can analyze our clusters of nodes and edges and get some understanding about the position in the network and also the relationship and importance of the internet connections between them. But these graphs don't just have to be people. They could be objects or classes in our source code or in our running applications. They could be devices. They could be ports or sockets. They could be rows in our databases or records that we hold. They could equally be service endpoints or API endpoints. And the edges don't have to be whether you like someone or not. They could be indicating ownership or a relationship between the two objects. They could indicate usage or a flow, a weight of a volume going between two objects, and indeed a link or a dependency. Or more importantly, they could be Kubernetes objects. And there's already been a lot of work done on this to visualize Kubernetes objects with graph databases. I'm going to show these examples in a little bit more detail. So on the left, we have something called KViz, which is a little project which will render your Kubernetes cluster as a graph. And then there are some other tools. So WeebScope might be one from Weaveworks that you might have heard of that allows you to view a lot of the workloads running on a Kubernetes cluster in a hierarchical form. And then there's a defunct Kubernetes plugin for Cockpit, which sadly is no longer maintained, but that would let you look at a workload in a graph format. So what have I found out by trying to analyze Kubernetes inside graph databases and a little bit beyond as well, and indeed visualize that information? So I'm going to do a demo now. Warning, it has got some fast-moving images, some flashing. If you're uncomfortable with that, I would advise you to skip the next 18 minutes worth of content because there is going to be some on the screen, demo gods permitting. Fortunately for me, Tim's just given a talk on some of the hierarchy of objects within Kubernetes, which is really handy. So we organize our workloads into namespaces, and we have pods that are controlled by intermediate objects, and they run on Kubernetes nodes. Okay, so we should all be familiar with that. We should all recognize that from Tim's example before. So let's flip over now to the demo and see what we have found out. So, okay, full disclosure, this is a video. I've done that for two reasons. One, there is less chance of the demo gods hating me, but also I know how long I'm going to take. So in this example here, we have KViz. So this is an open source project, and what it does is it connects to your Kubernetes cluster, and using a D3 force layout, which is a JavaScript library, the particular layout, it will render your cluster. And that was my Kubernetes cluster running in Docker for Desktop some time earlier. This is an article by someone who worked out how to pull Kubernetes objects into a big graph database called Neo4j. They use some extensions built into Neo4j to talk to the Kubernetes API, pull back all the objects, and then they could render them inside Neo4j. And we'll take a look at something very similar to that shortly. So this is Neo4j. This is the front end, which is just browser based, and behind the scenes running is a Docker container. Here I have exposed some ports, used a folder on my disk so that I've got persistence, and enabled some extensions, and that will just start up like that, and then I can point my web browser at it. Now, to get the objects in, I didn't use the extensions. I wrote some Go code. In fact, I wrote quite a lot of Go code, actually. And what this does is this uses the Kubernetes client, the Go client, to pull back all the nodes, namespaces, daemon sets, stateful sets, deployment replica sets, and all the workload objects from within Kubernetes, including services and the nodes that they run on, and also define the relationships between them. And they're sent over to Neo4j for later analysis. So I've already run this code in this example. And if we go over to Neo4j and we start with a little dig around, if I go into this bit, I can see I've got over 5,500 objects in there, and I've got over 7,000 relationships between those objects. Neo4j has a query language called Cypher, which is a bit like SQL for those that have used it. And I can ask Neo4j some questions about things that it's collected. So I can ask it sort of metric numbers, and I can do aggregate functions on those metric numbers as well, pretty much like you would do with a relational database. But I can also get it to pull back a visual representation. So here I'm asking it for the Trickster deployment. And what it does is it pulls back Trickster deployment and the objects connected to it. So the replica set and 2 pods. And if I click on the pod, I can see all the properties of the pod there. Now, where it gets useful is I can start exploring. So I can expand out these nodes. And if I expand out the Trickster deployment, I get 2 more replica sets. Obviously, they don't have pods because only 1 replica set has pods at a time. And I've got the namespace there. And I can keep going. So if I expand out the pod, I can see the node that it runs on, and I've got the service, which is also connected to the namespace, and I can do the same with the other pod. So there I can start exploring what my cluster looks like. I can start looking at the properties of each of those nodes. But I can ask it vague questions as well, which it gets really powerful. So I can say, find me the namespace objects and all the things between it that are connected to a particular pod. So I now get back the deployment, the replica set, the pod, the service, and the namespace that it exists in. And it would have pulled me that back, whether it was a stateful set, a daemon set, whatever. It would have pulled it back because it just went between the pod that I asked for and the namespace. And again, I can expand this out pretty much as I did before. I pretty much recreated what I had earlier, but let's expand out the namespace now, and I can start really expanding out what it is that everything's connected to. So I've got loads of other workloads here, and I can expand those, and I can keep going. And keep going and keep going and keep going. Equally, I could use the cipher language to pull things back. And there was a point where I have to kind of zoom out. And you can carry on going with this until there's a couple of thousand objects on the screen. But then Chrome starts to struggle a little with that because of the rendering engine in Chrome. So we have got kind of like a top-end limitation there. And under the hood, this rendering engine is using the D3 library, and it's using something called a force directed graph. D3 is a fantastic visualization library written by Mike Bostock, along with a load of other contributors, and this is an example of that force layout in a much simpler format. So we could plug this in and maybe get it to render quicker. Then I discovered this, which is similar to the force layout, but it runs in 3D and it uses WebGL to render. And it means it can perform with a lot more nodes. And I found this example on the Neo4j website, downloaded the source code, and actually it was really simple to tweak to get it to work. All I needed to do was change my connection string to my local Neo4j running in Docker, update the query to just pull back everything really. And I ran it, and it was quite spectacular, the results. So back came this. So what's happening here is in 3D, we are rendering 5,000 plus objects, and we can drag it around. And the layout that's applied is based on relationships between all those objects. And I thought this was really cool. And I did it one lunchtime just as a quick test. And before my workmates came back from lunch, I stuck it on a big screen in the office. When I came back, there was a mixed reaction. Some people thought it was one of the coolest things I've ever seen. And other people just said, well, it's great, but it's a hairball. I'm just going to pause the video a second. They're not alone in that opinion of it being a hairball. Martin Shinvinsky, he has a similar view of these kind of renders and recommends using different ways of displaying this information because he thinks the amount of noise versus signal in these renders means that you're missing the meaning. And he has some very good points. And Martin's rapidly becoming one of my most favorite people in data visualization. And he works with genome analysts for biological reasons. And his approach is really refreshing. He says, for example, this graph here is the same graph, just rotated and flipped, but it's the same thing. And in this example, there are that many different layouts. You can interpret the same data and get all sorts of different meanings out. And he used to be a systems analyst, so I really like his work. Okay, but I mentioned I did some data analysis courses a few years ago. One of the tools I came across to analyze those graphs of people and names was something called Gephi, which was a social network analysis tool. But it can handle a lot of data and visualize it really, really well, a lot of flexibility, and you can do a lot of investigative analysis on the data you load into it. So what I thought is if I pull the data out of Neo4j into here, I might find some meaning. So I start a little streaming server here, which is how Neo4j is going to connect to this rendering program. Then I need to run a little bit of code that's going to use an extension and send over all the objects and all the properties from Neo4j via the streaming API into Gephi. So if we start this, it's going to start whizzing and whirring. And what's actually happening in the background, if we flip back to Gephi, you will see all the objects and relationships arriving in the what's called the overview area. And you can see in the top right, there's a little count of the nodes and the edges. And by the power of video editing, we'll skip forward to the final amount. Now, it's just short of the number we wanted. We're a couple short, so there's something else we need to do. So we just go back into Neo4j, just check that. Yeah, we were about 16 objects short there and a couple of relationships. So again, I run a very similar query to the one that took over the main objects and everything connected together, which is basically the same, but there's a little knot in front of it. So this is kind of all the side objects that aren't connected to the main thing. So we want 5, 5, 6, 7 objects, nodes, and 7, 2, 3, 4 edges, and that's what we've got. So what have we got actually data-wise? Now, we can look at this like a spreadsheet that's inbuilt into Gephi. So we can go to this data laboratory view. So if we expand that out, we can see all the different objects there. If we scroll down, we can see all the different properties for all the different types of objects, because some columns are relevant for some objects, but not others. So there's a whole load of pods. So we've got our data in. That's great. We can see it all there. Let's lay it out. Let's make it look nice and try and find some meaning. So let's color them by the type of object. So let's apply that. I'll drag this little panel to the side so that you can see it. And you see immediately we've got 51% of this test cluster, which I took the data from at work, is replica sets. What I can do now is use a layout, and this is the woo moment, by the way, which will arrange all of these objects out of Kubernetes into a layout based on the relationships between them and what they're interlinked with. Let's expand that a little bit more. There we go. Okay, so what have we actually got here apart from a very interesting shape? Well, all those objects, again, what Tim was talking about earlier, we can see the deployments, we can see the replica sets there, we can see the namespace object, we can see that the one replica set has a pod, in this case, a little green dot down there, and that pod is connected in turn to a service, which is in turn connected to the namespace, which is in turn connected to a node somewhere in the middle of the cluster. So let's have a little zoom out of there. Unfortunately, this was a bit fiddly and I got the wrong one. No, it wasn't that one, but it illustrates the point. This one here, so there we've got the node in the middle of the cluster. And if I select that node, we can see all the pods that are running on that node. Have a looking around the rest of the cluster. We've got a kind of interesting shape at the top. I think we're going to do a lot more looking into that. And we've got some deployments with replica sets, but they're just connected to the namespace. We've got lots of workloads here without pods. We shall investigate that further. Now, what it would be useful to do is use some of these statistical analysis tools that are built into Gephi, but I'm not going to do that. What I'm going to do instead is I'm going to start filtering out the data and clean this up. So I use something called the partitioning tool in this filter, which I drag down to here. This is kind of like an if statement. And what it will do is it will hide certain objects from view. So if I filter out the node objects in this case, so these are the nodes where the Kubernetes pods run, and I filter those out, we can see some objects went away. If I lay out the cluster again, I'm going to get very different results. So suddenly we get all these different separated islands. And if we go and look at those, what we find are these are the Kubernetes namespaces and the workloads running within them. So we can turn on some labels so we can see what they are. So let's do that. And probably make them a bit bigger. Yeah. So I can see there that I've got some deployments, some replica sets, and some pods running there. That's interesting. That's a nice simple one, but some of them are much bigger and much more complicated, particularly this one up at the top. This is the one we looked at before. So this seems to have a whole load of workloads on it, but not a lot of actual work. But many of the other namespaces on here look very similar. We can see this one's got some jobs running. That's the orange color. And what we might want to do is think about looking at this a bit differently. Maybe we don't want to look at the namespaces. Maybe we should concern ourselves rather than workload, but with compute. So if I unselect them all and I just select the nodes and the pods, so these are the workloads and where they run, they get displayed. And if we lay it out again, we get a very different layout. There we go. So we got these little islands, which are the Kubernetes nodes running the workloads. Now we know that the workloads are the only thing running on those nodes, those pods. So why don't we color those based on the status of those pods? Maybe we'll find something interesting there. So we scroll down to status, and we can see the different states there. We can start to see immediately that we've got some nodes with lots of pods, but we've got some nodes with a few pods that are in failed state. That could be important. Maybe we need to go and look at that node and see what's the matter with it. Also, we can size them by any of the metrics. So I'm going to choose CPU request here. So out the requests and the resource limits, and size by those. And if I lay out again, I can now start to see where the workloads are being distributed, and fair play to the Kubernetes scheduler. It's done a good job of sharing things around. But I've also got a really big one here. What is this workload? And again, I can put the labels on it and zoom in. And maybe I want to go and find out more about that. Maybe go and dig around in Neo4j, or indeed use kubectl describe and get to work out what's going on. So that's exciting. There's another piece of Go code here which uses something called the shared informer object. So this is another bit of the Go client for Kubernetes. This pulls back all the objects in the order they're created, and it creates a log file. And basically, I left this running for a couple of hours, pulling back all the data and about the events that happen on the cluster. There's a lot of metrics data. I spoke to metric server and pulled back all the pod memory and CPU usage because I thought that might be useful. And then I saw a pattern in the data which it kept repeating. So there's something called the toggle namespace. And when I looked at it, I could see there was something amiss with what the events that were happening. There kept being these repeated patterns of relationships being added and then deleted and then added again. I saw that repeated throughout this log file. And I thought we might want to have a little look at what's going on there, because there's possibly something broken. Possibly. Now, to get this data into Gephi, it can import loads of different formats, including CSVs. But in this case, I'm going to use a graph exchange file, which is like an XML file. This piece of code is going to read through all those lines in that log file and construct me this file. Now, as I say, it's an XML file, and it's basically the structure of the objects and the relationships between those nodes. But also, if you look, you might see some timing information there, a start and an end. We'll look at that in more detail in a second. So let's pull that graph exchange file into Gephi. Here it comes. And so, okay, we've got a block of nodes. Let's color them by kind in this. I'll use that field name. And again, we've got, similar sort of, as you'd expect, cluster, but we've got an extra field in the data laboratory now. We've got this interval, which specifies when the object was created and when it died. So what that lets me do is that lets me do some point-in-time analysis on the data I've got. So let's lay it out again as we did before. We should see something very similar. Okay, it's the other way up, but same sort of graph. The observant ones amongst you will notice at the bottom of the screen there's a big button saying Enable Timeline. So if we click that, what that lets us do is narrow down the nodes we want to show on the screen out of a particular time range. So this is like about an hour's worth of data. And what I've done here is I've selected to size automatically by CPU metric. And if I hit play, that timeline moves, and we can see the pods in the cluster changing size as we move through time. So we've got point-in-time vision of what's actually going on in the cluster, almost like a kind of black box flight recorder. If I go and find that pesky toggle namespace, which was bugging me before, where are you? There you are. And I select it, I can find that in the overview. And if I go back to the overview, it's there on the left. And what you will see here, as we move the playback head along and change time, is there's a green line appearing and disappearing between the toggle DB service, that one there, and one of the pods. So if we move it along, it's appeared. Yeah, it's just there. You can see that there. That is indicating as we move the head that line appears and disappears. So there's probably a problem with that service and pod. Let's have a little bit of fun. Let's do something flashy. So if I arrange this set of cluster data, and this is from a Monday morning on our test cluster. This is a scale up. And what that means is if we enable the timeline, we can see what happens to our cluster as our users start scaling up their workloads on test. So if we hit the layout, we get our familiar view. But if I hit play, what we'll see is all the pods from the edge of the circle as they're being created, flying into the cluster and joining the workloads associated with the namespaces, which I think is kind of cool. Again, we can stop that and scrub the head backwards and forwards. But what if we view the same thing, but by this idea of looking at workloads? So if I take out the Kubernetes nodes and I run the layout again, yep, there we go. And now I hit play, we're going to see the workloads fly in, the pods fly in as they're created in the objects and go to the relevant workload, which is kind of cool. But again, what we might want to do is view this by compute. We might want to look at how this looks with just the nodes and the pods. So again, we lay out in a circle, we change the time window, we select the objects we want, so the pods and the nodes. That's filtered, and we run the layout on a small bit of graph. And then we can watch what happens as the cluster's being scaled up. Now, I'm just going to hit pause a second, because somewhere around here, you're going to see a node being created. So this is an elastic environment. So there's going to be a node created, and you'll see the workloads arrive on it. So if you look closely at that area I was just pointing at, and sort of mid-top, here comes the node now, and the workloads get scheduled onto it. I think that's kind of useful and kind of cool as well. Now, there are other layouts as well. It's not just all this this layout here. This is a hierarchical one, which I'm going to sort by the type and by the namespace, and that will arrange all the different object types by the by namespace. So what I can do as well is size. If I do that and relay it out, I quite like it on black as well, this one. You can start seeing the namespaces and the green pods, and you can start seeing which namespace is using the most stuff. So there's also this preview option as well, which will render out a nice vector version of the image as well. So you can print it off and give it to a loved one as a gift, if that's what you want to do. But yeah, very interesting stuff. This is another demo. This is a parallel coordinates graph written in D3. This is all the pod data taken out of Neo4j and plotted as lines across the different dimensions, so we could start to see common patterns across the data. So it's not just about Gephi, there's many other ways to visualize data in the cluster. So that's the end of the demo. Okay, let's move on back to the slide deck. So there was lots of stuff there, and you saw some of the learnings we got from it there. What did we really find out? Well, one of the important things I think we took away from it, and actually reassuring, was our live clusters are really quite boring. There's nothing interesting or unique about the workloads on there. They all pretty much look like one another. Test clusters, however, I'm very pleased to say, because we want our teams that use our cluster to have to experiment and have this learning culture. So we found a few things there. Some of the things were a little bit weird, but some of them were actually quite reassuring. So this was the first thing we found, and this was one of the very early renders I did. This is actually for Neo4j. I didn't have quite the amount of data in this cluster at this point. But you can see these yellow daisies on there that are indicating that something strange is happening. And what they are deployments with replica sets with no actual pods associated with them. And when we went digging around, we found that we had a learning opportunity for everybody, because somebody had increased the number of revision history limits from 10 to a lot. Fortunately, we were able to get that tidied up. But yeah, it was one of the first things we found. And it's obviously somebody thought that was a good idea at some point. And that's fair enough. It is a test cluster. Then in Neo4j, so not even in the swanky tools, I was alluded earlier to the idea of asking vague questions to Neo4j. So we saw the example where you could give Neo4j a query saying, find me the namespace and all the objects between it and this particular pod. Well, we can do very similar things with Cypher as well. This was finding all the services by namespace that didn't have any pods connected to them or connect to any pods. So we've got some authent services here. So we can take this, export it as a list even, and then go and talk to the teams about what is actually going on here. And the idea of grouping, it was interesting. This is the cluster, but with the pod size by CPU and memory requests. And what I'm looking for here is seeing if there's any connection between heavy users of our cluster, be that on CPU or be that memory. And that allows us to then go and investigate on those pods and the associated namespaces and find out if someone's been a bit noisy, for example. Warning, the Kubernetes API does lie to you. We asked it a question. It brought back that these two particular pods here were requesting 1 million terabytes of RAM. Now, our clusters don't have 1 million terabytes of RAM, unfortunately. And in fact, they were really requesting 1.2 gigabytes. But the API decided to return us the wrong number. So probably a bug I should file on that one. And we spoke about the hairball and the this interesting namespace in the cluster. Well, I did some analysis on this. So I split them in two and did the same investigation on both. So the first thing you do is filter out all of the noise, get rid of all the unused replica sets and deployments and services that aren't connected to anything, and it dramatically decreases the number of nodes and edges that we're working with. And although the hairball on the left still looks like a hairball, it's a much smaller one and there's a lot more structure to it. When we looked at this interesting namespace, we discovered that actually this was really well managed. The team looking after this namespace was scaling things up and scaling things down as they needed them. And that's why there were so many what looked like unused bits of workload there. But actually, that was the way the team managed the workload. This is a filtered version of the cluster. So this is with all the irrelevant stuff out that hasn't got any workloads associated with it. And we've sized them here by age, which is something we've not thought of before. And then if we filter that down by replica set, we could see there were some quite large replica sets there, indicating they were quite old. Now, that meant we could go to teams and ask, why are your replica sets so old? You know, are you cycling these? Are you using the same tag to redeploy stuff? Or have we got some old code running in the cluster? We can have grown-up conversations with the team about that. In this next example, we've sized by the restarts and colored by status. What this may indicate is that we've got some nodes which have got some really heavy workloads on, but also looking at the colors, we can possibly work out there might be a problem with a node. There might be a lot of restarts on that node. And if we size it by the request and then again color by status, we can clearly see that some of the workloads might have problems. There might be some namespaces that have workloads that are failing. We can go and ask teams about those as well. And equally, this is sized by CPU request, but colored by status. And we can see that the failed workloads on those namespaces. And in fact, I missed a bit on that previous example. On the right-hand side, on this example where we were looking at workloads, we've got some pods off to the right-hand side, which are in pending state. Now, this could be just at the time we took the snapshot of the data off the cluster. These pods were in pending state. But if they've been there for a while, that might indicate there's a problem with the scheduling or maybe the affinity rules those pods have got, or even there might be a resource contention issue. So we could go and look at that. Sometimes Gephi teases me. I lost a whole morning to this. I had 3 nodes in the cluster at the top, which looked like they were surrounded by question marks, teasing me. And I spent some time trying to work out why these 3 nodes had very different workloads to the rest of the cluster. And then I remember we use Bootkube and we run our control plane inside our cluster. And this was actually the control plane. So, yeah, don't necessarily get drawn into investigations which aren't needed. And this was another reaction that I had. I saw the cluster with obviously a large workload off to the bottom, surrounding a single node. And the lesson from this was when you see an anomaly, don't assume it's bad, and also pay attention to stand up, because this turned out to be somebody load testing a node on the cluster, which I actually knew about. Anyway, so they're the lessons we've learned from all this analysis on the cluster. What are we going to do next? Because this isn't finished. Well, there are obviously a ton of other Kubernetes objects we can look at. We can look at the node data. We've got that. We can pull more real-time information in from Prometheus on the metric server that we run. We can look at the usage of storage and config maps and configuration. But we can also look at things like RBAC and the permissions on the cluster. What has permission to talk to what could be really interesting. And obviously there's network stuff. Now, network policies, the services, and we run Istio for some workloads, so we've got a lot of service mesh information there in telemetry. We weren't the first person to render network information. This is Jack from Monzo. I had a brief conversation on Twitter with him through a mutual friend, and he was explaining that at this point in October or November when I spoke to him, they were just rendering out the relationships between the network rules in Gephi as well, as it turned out. So that's something we can certainly do off our cluster. And this is a relatively new talk that got published last week by Nikki Watt, who's CTO at OpenCreode. Now, I mentioned that Gephi has some tools to do what we call graph theory or social network analysis. So being able to find the relevance of the position of a node within a network, understanding its importance or its centrality, but also identifying communities and groups of certain workloads within it. Well, Nikki explains using Neo4j that they have looked at some connection data taken from Kubernetes of a microservices architecture and worked out ways to analyze and improve the actual architecture of solutions. I'd advise you to watch that. It's really interesting what Nikki and her team have done. But before you all run away and download Gephi, I think it's fair to say that in its current form, I'm not sure where it's going next. The development team here who've been working on Gephi for the last best part of 10 years I've been very open about what they're going to go with it next. They gave talks at FOSDEM about it, actually, and they've also put plenty of blog posts on the Gephi blog as well. So it may or may not be around in its current form for who knows how long. But if you want to get started with this, there's a ton of links I've put in the resource slides towards the back of this presentation as well. And I started working with D3 towards the end. I started doing the parallel coordinates graph in the bottom right. But D3 is really powerful. And there's also like a whole range of examples on the Observable HQ, which is done by Mike Bostock. Really powerful stuff. It might work really well, although I have to write more code to do investigations rather than interactively filtering things out, but I might get some really interesting results. And I like the idea of putting this stuff in notebooks. So something like Jupyter or Shiny might be a really good way to share this information with people that are using the clusters rather than saying, we spotted a problem, why not send them a visual representation of it? And because I am a big proponent of DevOps, this idea of removing the wall between the dev team and the operations team and collaborating and having shared responsibilities, I think that would be a real enabler for that. And we certainly do the DevOps thing within our team. There's a book on it here. I love this book for two reasons. Number one, Skybet and Gaming are in it as an example, but also it analyzes things down to 4 key types of team. And we've already kind of restructured the squad I work into to have these kind of teams within it. So my team is concerned with engaging and empowering and supporting the people that use our cluster. So we're kind of a DevRel team. And the work which we've been doing in this L&D activity is certainly something that's given us a whole load of insight. So let's wrap up. In summary, have I solved this problem that was highlighted in the Stellar report? Locally, we've learned a lot. Have we shared this? Have we made it in a way that people outside of the team can learn from it? Have we made a product? Not yet, no, but I think the start of it's there. But it's definitely feeding into the enabling team and focusing the kind of things we're trying to do with the other teams. It's given us a massive understanding. This idea of having the data in a database and a source of truth and being able to ask it questions is really, really powerful. It's really useful because we've not really had that before in one place where we can do aggregated queries on it, and we're finding out a lot from it. But also this idea of doing point-in-time analysis where we've got a log of cluster activity. We will probably start recording these logs out so that we can pull them into something like Gephi and review the state of clusters at points in time. We think that's going to be really, really helpful trying to understand what happens in incidents, particularly when we're not looking at the cluster. So looking at the state of cluster before an incident, during an incident, and afterwards, I think it's going to be really, really useful. So we're probably going do something with that. And then in terms of just the idea of visualizing complex systems and sort of abstracting away from Kubernetes for a second, the data in a complex system has many, many dimensions. And I think the hairballness of the visualizations we get out of them indicate that this is complex and that there is complexity there. But I find if you remove as much noise as you can and you can separate the patterns from the randomness or the signal from the noise, you can get some real understanding. And if you have a context or a perspective to look at this information from, so whether it's workload or compute, as I've demonstrated in the examples, or if we expand this out looking at connections between nodes, so that network and security information, and then combining those perspectives again, I think we're going to understand the cluster even better and understand the workloads that are running on it. And just one more thing. I hope that's given you some idea into how to go and visualize your clusters. All the links that and all the references to all the stuff in this presentation are on the next couple of slides. So you have references here to all the talks and the tools, some tutorials on how to use Gephi, some books that I've used throughout this, the Go source code, and all the other examples which I've referenced. And with that, I'm slightly over, but I hope you found that useful, and thank you very much for watching. Thank you.
Thanks, Andy. That was
Thanks, Andy.
mind-blowing. I have to say that's an absolutely brilliant presentation there, and you know, my literally my jaw was dropping at parts of that. That's full-on Minority Report level level monitoring work there. I particularly really loved how you actually got to the point of getting real insights out of the data there. You know, because I mean, I've seen lots of people do these kind of analysis, not to quite to that extent, but you know, I remember seeing similar things in large OpenStack clusters, right, Nick, that people were doing kind of visualization analysis. But it's where you can actually go, and this taught us this that we couldn't have seen in any other way of looking at that data. I just think is absolutely phenomenal.
Yeah, cheers. It's been an eye opener. I mean, it's you know, I think if you're watching this now and you're thinking, what does the stuff that runs on my cluster work like? What does it look like? I don't think you would have an idea, and certainly what came out of it was nothing like I expected. And it's given us a much better understanding of what teams are using it for and how they're using it as well. It's just been like the main learning from it.
Yeah, I mean, I guess the next stage of these kind of approaches to operations is you know, how do we use that in a real time context, right? You know, as opposed to, which I think you were alluding to towards the end of that talk.
Yeah, I haven't worked out of how we can kind of like, I mean, so you kind of brainstorm these ideas with your colleagues, and one of them was like, can we have it real time on a screen of what it looks like? And it's kind of, actually that's quite tricky to do. It's not impossible, but because of the way the Kubernetes API works, you're kind of like, you get everything at once at the beginning and then updates to it, and quite how you would be able to say, you know, keep that going, or can we like refresh it now? A little bit tricky, but maybe somebody's got some better ideas.
So folks, if you want to ask Andy questions, please do so in the comments. I know Andy can see the comments from this end as well, but please do feel free to post. We've got a few more minutes to take some more questions. So Andy, the other I saw recently some really interesting work that's in Grimoire Lab, which is the open source tooling to look at open source communities and to start looking at metrics around open source communities. And there was some fantastically interesting stuff in there using this same kind of tools about analyzing multiple open source projects and showing the connections between people across multiple open source projects, which actually gives you a lot of insight about, you know, who are the potential influential people within a group of open source projects. So when you look at something like the cloud native ecosystem, for example, you might be very interested to work out which individuals are contributing across a wide range of projects, and that was also super interesting.
The graph theory and the social network analysis stuff is really powerful, particularly when you're talking about people. But although I haven't used it too much in this example, but the talk I referenced by Nicky Watt was fantastic. Yeah. The way they kind of track that interaction between the components of the system, like a network of communications, and then analysed what was talking to that and how often, and it was a bit mind blowing as to what you can find out and the learnings they got from that as well.
Absolutely.
So Andy, I wonder, and this is to build on what's already like a substantial piece of work, but I wonder if do you think it's feasible to track service accounts and to track the way that those service accounts call things outside the cluster? To give you a bit more of an idea about what I have in mind, let's say you've got a pod that's got a service account, and it exchanges its service account credentials to call, a cloud provider API for maybe like a object storage. I think that would be a great idea, but maybe you think it's feasible. Maybe it's tons more effort. I'd be interested to hear your perspective.
Off the top of my head, I can't think of a way how you'd identify the pod and the service account. That's fine. How you would tie that into an actual network connection, and maybe some form of rule in a network policy or something, that might be a way to do it.
I was thinking either cloud audit logs in GCP or CloudTrail in AWS, and be able to process that to become part of the graph.
Yeah, and again, just to reference Nicky's talk, they actually took the data off the service mesh. They were using all the telemetry info on there of what was talking to what. So if you combine that with which service account was running on what pod, which talked to what thing, then in theory you could work that out. Yeah, that sounds feasible.
Cool.
Is that so you can work out who's running up the bill?
I think the sort of the next thing you would add would be like, and this is in this cost this cost center or whatever. Yeah, it could be useful for that.
Yeah. Does anybody have any more questions? Some familiar names in the chat channel there. Oh, good representation from the Stockport area. Thanks for being here.
Okay, well, I guess then that's the end of tonight's proceedings. Thank you very much, Tim and Andy. Enjoyed both of your talks very much. Oh, hang on, we've got a question coming in. Question from James. Andy, have you seen any teams make different architectural decisions after seeing complexity?
No, is the honest answer. So the reason I say that is we haven't found what we found is these discoveries can change the questions we ask teams. What we haven't got yet is a way to make these some sort of formal report or productize it into a way we can go and show people and say, point at it as to what is this, that kind of thing. If people wanted the data to look at, we could obviously let them look at that internally. But as a delivery mechanism, and that was one of the reasons I was alluding to things like Jupyter Notebooks and Shiny, which is a way of kind of like interactive in-browser code, but querying the data. I think that could be really powerful to kind of, say, this is what your bit of the cluster looks like. What do you think to this? I know when Dave White was at the last meetup from Auto Trader, they looked like they had something very similar to KViz in their dashboarding tool. It may even be KViz, I don't know. But that I thought would be a really good place to put that data. I really like that idea. So one of the things we're going to start looking at next is maybe some dashboarding tooling anyway, so we might integrate it with that.
I suppose you need to get to a point where you can tease out, you've got this richness of data and the fantastic visualizations, but then being able to tease out the things that teams would respond to in terms of making architectural changes. So things like, oh, it's costing this amount of money. We didn't realize it was costing this much because there's this complicated stuff that's happening under the hood. Or, the fact that our application falls apart all the time makes sense because we didn't realize that it was this complicated, that kind of thing.
Yeah, and I think you've got that. If we could pull in that, data about network connectivity through maybe something like the open tracing metrics or something like that, where we could demonstrate a lot of connections between different bits of the system. I think that might be powerful because that, I didn't know it worked like that. I didn't know that spoke to that. Why does that speak to that? And why does it speak to that many times as well? Because we can as well in these graph tools render the size of the connectivity. We can do that as a visual arrow, so we can make it quite bold or wide, indicating where there's more traffic going.
Yeah, cool stuff.
Okay. Well, again, thanks to Tim and Andy. Thanks to everybody who's watched live on the stream. And thank you to all of our employers for letting us talk about the interesting stuff we're doing. So that's D2IQ.
What else are you going to do during a lockdown? There's nothing else to do. I've watched everything on TV. I've finished Netflix. I've finished Amazon. We'll be really interested in getting people's feedback from tonight as well. Obviously, if folks agree that this format has been a success, then we can look to get another one lined up at some point fairly soonish. We'll be really interested to hear your feedback, so feel free to shoot us an email. Reminder as well, there is also a Cloud Native Manchester channel on the Kubernetes Slack. In fact, there's even a meetup on the Cloud Native Slack as well, if anyone uses that. But yeah, Meetup Manchester on the Kubernetes Slack. We're on there if you want to ping us with any more, with any bits of feedback or any ideas that you've got.
All the communication channels. So yeah, I mean, we're pretty sure we'll be doing one of these again, at least in the next month. So do subscribe below in YouTube. You can follow us on Twitter at CloudNativeMCR, and we'll also be announcing these on the meetup.com page. So thanks, folks, and that's good night.
Yeah, nice one. Thanks, all. Take care.
Bye.